2x2 table. The chest pain data set. Come on, one more. The p-value from that table was 0.55, 5051, bigger than 0.05. So if your confidence interval contains the null value, your p-value should be bigger than 0.05. Likewise, if your confidence interval does not contain the null value, then your p-value should be less than 0.05. So qualitatively, you can get an idea about whether a p-value is significant or non-significant just by looking to see if the confidence interval contains or doesn't contain the null value for the association measure you choose. So that's some general comments about tests of significance and confidence intervals as applied to 2x2 tables. Just very briefly, if you have a continuous outcome, instead of using a chi-squared test, you use a t-test. For example, here's some data looking at 47 asthmatic patients who were smokers and 180 asthmatic patients who were not smokers, either being ex-smokers or never smokers, looking at a measure of their physical function, number called the physical component summary from an instrument known as the SF-36. It's a number that ranges from 0 if you have poor physical health to 100 if you have excellent physical health. And what the t-test is going to do is compare the average physical function in the smokers to the average in the non-smokers. Now, the null hypothesis is going to say that those two averages are the same, so their difference is going to be equal to 0. The t-test statistic itself, the t-value, is going to look at the observed difference in their two means, the average physical function score on the smokers minus the non-smokers, compare it to what would be expected if the null hypothesis is true, which is 0, and take the difference in between the observed difference and the expected difference and divide by this a standard error number. Standard error is going to be a reflection of how common how variable the outcomes are in the two groups you're comparing, and also your sample size. The t-test assumes that you have an outcome which is normally distributed with a common standard deviation in the two groups. If the data set is large, these assumptions are not as critical. Just in passing, an analysis of variance is a method to compare not two groups, but three groups. So the t-test is a special case for an analysis of variance when you have just two groups to compare. But just briefly to show you how it works, in these data, this is a slightly different data set. There are 53 smokers. Their average physical function score was 41. The non-smokers had an average physical function score of 46. Standard deviation of the 53 physical function scores among the smokers was 12.6, 11.11 for the non-smokers. If you calculate the value for the t-statistic, you get a number of minus 2.75. And just like what we did for the 2x2 table, the way we determine whether this is a statistical result, the way we determine whether the data supports the null hypothesis, is by asking whether this number, minus 2.7, is a typical value for a t-statistic when the null hypothesis is true. So we look this number up in a table in the back of a statistics book. We look it up in a t-table. We see how often do we get numbers as extreme as minus 2.7, and numbers smaller than minus 2.7, or bigger than a positive 2.7. That happens very seldom, only 0.006% of the time, 0.6% of the time. 6 times out of 1,000 times when the null hypothesis is true, will you get data like this. So this data does not support the null hypothesis. That's what this small p-value is reflecting. Then finally, if you have an ordinal outcome, here's the same data, you use something called a non-parametric test. The most common is something called the Wilcoxon ranked sum test. And what that does is says, take everybody, look at their ordinal outcome, and rank them from highest to lowest, line people up against the wall by their outcomes. And now the null hypothesis says if you do so and you ask all the smokers to take one step to the right, all the non-smokers to take one step to the left, that the average of those ranks that those people had in the line would be similar. Otherwise, if the null hypothesis were not true, the smokers might be at the top of the line, the non-smokers in the bottom of the line, and therefore the average ranks of those two groups would not be similar. So to see how a Wilcoxon test works, here's that same data set, looking at an ordinal outcome, asking them about their changes in their severity of asthma. ranging from being much worse to much better. Here's the distribution of the people who are smokers in the top row, the non-smokers in the bottom row. Notice more of the better and much better are made up of the non-smokers. So most of the non-smokers are shifted towards the better, much better spectrum of the scale. Most of the smokers are shifted towards the bottom half. When we ask people to line up in a single line with all the much worse people first in line, all the worst people next, all the about the same in the next, followed by the better, followed by the much better, and then say all the smokers take a step to the left and all the non-smokers take a step to the right. Most of the people on the top of the line are going to be going to the right. More of the people on the bottom of the line are going to go to the left. Well, you can analyze this by a chi-squared test. That wouldn't take this order into account. You can analyze it by a t-test. It might not reflect, the numbers might not reflect distances, so that test might not be appropriate to use. But the Wilcoxon test will allow you to look at the ranks of those two groups, and in this happy to try to answer questions individually. But what I wanted to do today is just give you a feeling of how tests of significance are done, what a p-value means, what a confidence interval means. That's why I spent most of my time looking at the binary outcome. Well, let's see. I've got 1 minute left, so I managed to get through most of my slides, and that was one of the comments that people have. So I'm going to try to cut back on the number of slides we'll be showing. Another comment people did in the last evaluation we sent out is they'd like me to talk about sample sizes and power. We'll do that also. But what I'd like you to do now for next week is just think about the general points I raised. Erin's going to be sending you a very brief multiple choice quiz. I think there are 8 questions. So if you would just take them, send them to her, that'll give us an idea of whether we're all on the same page. They're just going to ask you about the interpretations of p-values and confidence. So that's where I think we stand. I'm going to stop now. And if Erin or Mona or Madra or anybody can turn on a microphone, have any announcements to do, they can do so. Otherwise, I have it as 5:30 here, guys, in Boston time, and your day's beginning out in Hawaii. A little bit later in the day in Alaska, so I'm going to let you guys go and do your thing. And next week, we're going to try to talk about modeling. So, that note, send me questions if you have any. I think we're running out of our time. So I'm going to stop talking right now. I'll stay on line if anyone wants some kind of question now. Otherwise, send me to them anytime. I'll respond to you. Have a great day, everybody. Erin, I'll hang on for a few minutes. Erin, I won't be able to hear you again. I can see your lips moving, but if you want to turn your microphone. Hi, Erin.
You want to turn your microphone?
I hear you.
Hi, Fred.
But I can.
Hi, Erin.
I'm going to stop